All right, hello everybody. I just turned it on, Michael. Can you hear me now? We're gonna give it another minute. There we go. All right, all right, all right, all right, all right. We're gonna give it another minute to get other people in here. So last week we got into a really sweet spot of this journey together, and I'm tonight I'm going to take you through a really great, I guess, phase of discovery, and that is that this section that we're going into tends to get a lot of people hung up that try to study on their own, and they end up just committing these answers to memory. And that's not a bad thing, but I think I've got a great way. I didn't come up with it, it's well known, but I think it's going to help out quite a bit. That it's to do with the math of the test. And I hope that when you walk away tonight, that you just have this light bulb moment, like that it becomes encouragement for you. That we kind of knock down a wall of intimidation, I guess, and get over a big hurdle that a lot of people, they really fear the math on it. Other people, they don't have that problem with the math. So, but I think we're going to get to a really good spot tonight. We're wrapping up section 5, and so we're on week 6. We've got 2 more weeks. I'm willing to go for a 9th week if we need to. I will tell you that there probably will be a section towards, so I think there's 10 sections altogether, 1 through 9, and then 0, which I guess is 10. And as we stand right now at 8 weeks, we're going to end up missing probably the last section. So I'm willing to go for 9 if you guys are. And I'll probably add that to the tail end. You won't get a notification or anything. You won't have to re-register. I'll just create another episode, and you'll still get the same invites, that you've been getting and stuff. So I did not go in, and I believe it says week 5 on there, maybe on your invites and your replays. I'm sorry, I have to go in each week and change that, and it's just been a really crazy week at work. I've had a lot of systems. I'm in IT, so I've had a lot of systems issues. So I've had to kind of work through and stuff. So, anyways, yeah, I mean, I'm willing to go to 9. I mean, like I said, we all set on this journey together, and I want to see it through to the end. And but I've managed to leave off the last section in the past, and people didn't have any problem passing the test. So anyways, let's go ahead and get through the math portion of this, and I really think that it'll become a little bit easier as we keep going along in this. If you've got the stamina for it, I've got the energy for us to do it together. So with that said, I see the same. So KC, you were in my last class, and you're still working towards it, huh? I remember. I mean, the name stands out to me. I remember you were in my class in the spring. So let's pull that trigger, okay? Let's get over that hump and let's get this done and start enjoying the hobby, I guess. So with that said, you're going to get questions that involve calculating power, how to calculate voltage, and how to calculate current, as well as resistance. And it's a really easy, when you see this, it is really super easy. and we'll go through the examples and you'll see why. So, you know, one of the things you just have to remember is that, you know, it's like ohms tightening up a tunnel. Volts is what is pushing the amps through. You know, amps are what'll kill you. A higher amperage of a line is really what's going to kill you. You stick a fork in an outlet, it's going to shock you. You go outside to your outside panel and put your hand on it. And, you know, the difference between a 200 amp service and you know, maybe 15 amps at the most. Most wall outlets you're looking at maybe 10 amps to 15 amps. That won't kill you. But well, it can put a serious it can light your world up. 200 amps, yeah, that'll definitely you won't even know what hit you. It'll fry you from the inside out. So just try to commit this to memory, you know, this picture. But with that said, we have what we call Ohm's law. Now when you go and take your test, you're going to be given a blank piece of paper. And on that piece of paper, before the test ever starts, I always encourage you to commit to memory the things. You can't walk in with a piece of paper and, you know, like a cheat sheet or anything like that. Everything you do has to be created at the time when you walk into the test. So if you draw two circles and draw them exactly like this, EIR and PIE, you do that and you're going to potentially, it will enable you to be able to answer at least, there's at least 4 questions. 4 questions that involve, usually there's about 4. Some tests have 3, but usually there's no more than 4 questions that involve Ohm's law. Okay, so, and the way this works is again, you'll catch this on replay, but you want to draw these 2 circles. And what you're doing, if you can get an eye on this, this is where we left off last week, but I wanted to step back a few slides. Whatever they're asking for, so if they're asking how much current would you get if, and they offer you the wattage and they offer you the voltage, you would just cover up the current, the amps that they provide. And as you can see here, if you were looking for amps, it would be a fraction, okay? It would be the wattage divided by the voltage. If they gave you the wattage, or they asked you how many watts would be in so many volts and so many amps, as you can see here, it's multiplication, it's side by side. Whoops, let's go back for a second. And once you see this, it's just real easy. I mean, so you ask, which one would I use? Well, if the question does not involve ohms, if they're not asking you for ohms and they don't provide ohms, then you're using the pi chart. That's your trigger right there to know which one you use. Okay? One of them is watts. Is if it mentions watts, you're using one of them, or if it asks for watts or one of the numbers they give you is wattage, you would use the PIE. And if it's ohms, anywhere in that question mentions ohms, you would use the EIR. And when you look at this, think about it again. If they were asking for how many ohms would there be on a line that has so many volts and so many amps, by putting your thumb over or your forefinger over the R for the ohms that they're asking for, that's you want to put your thumb over the missing, what they're asking you to find, how many of this, that's when you put your thumb over. And it really tells you whether or not, you just look at it and it'll tell you whether you're dividing or whether or not you're multiplying, right? Yeah, and Melinda, I take no ownership of. That's the reason why you're taking the classes. Is that yeah? I mean, I didn't create this. Don't get me wrong. I wish I did, but it's out there. Many different manuals use this technique. One of the reasons why I do not like the ARRL book is because they don't use this. They just put it out in words for you, and I just think that that's why I'm not a fan of the ARRL book. There's so many other books. The one that I recommended to you guys was Gordon West. You're always welcome to get it. It's Gordon West. He goes by, his nickname is Gordo. Gordo is what he's been known in the industry as. So I think he makes the best. He uses more graphs, more pictures in his book and stuff like this. So let's go ahead and get into it. Let's to see this is one thing. When I start doing it, it's going to make so much sense to you. So it says how much power. Okay, so automatically you're going to use the pi one, right? How much power is being used in a circuit when the applied voltage is 13.8? Now, if you remember, that voltage is what your car is. 13.8 is the medium, is basically your car voltage. I know it says 12 volt, but 13.8 is about the medium range of a good charged battery in a car. And the current is 8 amps. So they say it's 138 watts. Now, how did they come up with that answer? It's real simple. So they're asking you how many watts would you have in a line that has 13.8 volts applied and an amperage of 10 amps. Whoops. Sorry. So immediately I know that I need to put my thumb over the P for power, for wattage. Only one of these is going to cause me to put my finger over it, so I automatically know the other two that they give me. Now, how do you remember which one's E, which one is I, and which one is P? Okay. Well, you have to discipline yourself to know that watts means power, P, power. E is volts. You remember EMF, electromotive force, EMF? And the I for amperage or current, I really don't have one for that. I don't have I guess it's the last one left, right? And it's going to apply to the other graph as well. Okay. So let's go ahead and look at it. I mean, P, the power, they want to know how much power wattage would you get with the given volts and amps that they provide. Multiply that, 13.8 times 10, 138 watts. Okay, we're going to do another one. We're going to do a couple of these. Not all these are going to be on the test, just remember that. But with enough examples, I think you got this. So how much power, again, we're using the same equation. Power equals E times I, right? Volts times amps. How much power is being used in a circuit that has a voltage of 12 volt and an amperage of 2.5? Well, we know we're going to multiply these. And how do we know that? Again, we're using this particular equation because they're asking for the wattage and the power. So by doing that, the power, you have power equals E times I, or voltage times amps. They gave you 12 volts and 2.5 amps. Multiply those together and you get 30 watts. It goes back to the answer being 30 watts, right? Now this one, we're changing up a little bit. Now they want to know how many amps are flowing in a circuit when the voltage is 12 and the load is 120 watts. So we know that we need to cover up the I, right? We need to put our thumb on the I. The I is for current, which is amps. We're using this one now. Putting our thumb over the I, we know that we're going to, exactly, Beth, it really just, it's right there for you, right? I mean, it's just there. So they give you, it's power, the watts divided by the volts. They give you 120 watts, and they give you 12 volts. It would come up to 10 amps, and that's how they arrived at 10 amps. No, Paul, good question. No, it does not. The only difference between the AC and DC is that the direction of the power goes one way in direct current, and alternating, it alternates back and forth very quickly. But you would use the same math to get to the same place, derive at the same answer. So let's get another one. So what is impedance? So it's a measure of the opposition to AC current flow in a circuit. Okay, and the best way to really remember that is when you impede something. When you're impeding something, you're opposing it, right? When you impede somebody's entry into a building, you're opposing their entry. So the inverse of resistance is conductance. So we know that's not the answer. The inverse of resistance is conductance. The measure of Q is something covered in the general and extra exams. It's too deep for this, and it's just meant to throw you off, okay? Power handling capability. So power is measured in watts. So the power handling capability would be rated in watts. So components they're rated in things like watts and volts and even amps, but none of these things are called impedance. So it's just not the answer. And that leaves it as a measure of the opposition to AC current flow in the circuit. And impedance, so impedance, opposition, resistance, they all have the same, they all mean the same thing, right? And ironically, those all have a unit. So the unit of measure would be ohms. Okay, so impedance, resistance, and opposition would all be the same, would have the same effect. So what is the unit of impedance? Okay, so we know that volts is so impedance is actually very similar to resistance in many ways, which makes sense since impede and resist are roughly synonymous. Thus, it makes sense that they share the same unit ohms. The main difference between resistance and impedance is that impedance changes with frequency. Okay, so, and this is a very important point to tell you that feed line, coax, the wire that you go between your radio and the antenna, you can't, there's no such thing as a one-all, do-all wire, okay? Coax works at certain frequencies better than others, okay? So you wouldn't use the same coax to use on HF that is 30 megahertz or lower. You wouldn't use on VHF or UHF. You may get away, and what happens, it doesn't blow up your radio, it just creates more loss. Okay? So there's more resistance on that line, and what it does is it causes the power to be reflected back. What is it called when power gets reflected back to your radio? It's SWRs, right? Standing wave ratio. And what the radio does is it powers back some to protect itself. So a perfectly tuned circuit where you have an antenna that is a resonant antenna for the frequency you on. It's the antennas of a length that is what we would call the sweet spot. And the coax is always going to have some level of resistance to it, always. So, you know, it's a kind of a funny analogy, but I will tell you that depending on where you live, some people believe that you should put all your money in the rims and in the stereo. Some people will tell you all the quality of your vehicle needs to be in the transmission. Anybody with a four-wheel drive will tell you the transmission is the heart and soul, all right, because it distributes the power from the engine. Well, when you're buying a radio setup, you want your coax. Your coax needs to be the highest quality coax. Coax isn't cheap. Coax can run anywhere from 30 cents a foot to $5 a foot. You know, RG8X is probably about 30 cents a foot. Stuff called Heliax. Heliax is it's actually got a solid core spiral winding that goes around it as a shield. You can't even bend it. It's just that stiff. That stuff runs several dollars a foot. I prefer what we call LMR 400. So LMR, I'm going to type it I prefer LMR 400. LMR 400 can be used basically on anything. If I were to give you, there is no such thing as a one-all do-all coax, but I would say LMR 400 it comes close. I can use LMR 400 on just about everything. And the losses are negotiable. I can deal with the losses, the signal loss. I'm going to lose a little bit of wattage in my signal. I'm okay with that with LMR 400. LMR 400, typically $1.25, $1.30 a foot. I can get it for about 70 cents a foot. And you could too. I don't have a special. You just got to shop. And when you find that one supplier, you just kind of stick with them. I don't have any special deal or a backroom endorsement or anything like that. I just have a supplier that I know is pretty cheap. And he doesn't sell. So every coax there is a brand manufacturer out there. So LMR 400, the best stuff out there is made by a company called Times Microwave. That's just the name of the company, Times Microwave. But there's several knockoffs that the quality is just as good as Times Microwave brand. So the stuff that I buy is it's called Andrews, and I would put it up against Times Microwave any day. You know, and at the end of the day, I guess it comes down to kind of like, what's the difference between Quaker State and Mobil One? There's a difference, but most people don't really care. You know, so anyways, I could go on and on with that one. So inductors pass direct current, but have a higher impedance the higher the frequency, since inductors tend to resist changes in current. Capacitors have infinite impedance with DC, with direct current, and the higher the frequency, the lower the impedance. You don't really need to know that. I just, some of this is just a little added information to give you substance. And that's what I try to do in all these, is try to add a little bit more substance to it. Sometimes, yeah, there is such thing as getting too much information, but what's worse, too much or not enough? So, and some people pick up on different things than others. So, so what is the proper abbreviation for megahertz? Personally, if you get this wrong, you probably shouldn't be in ham radio. I mean, however, look at the answers. They're all MHz, but which ones? So I would say the closest is between A and D. Okay, you want your hertz. The H is always going to be capitalized. Okay, always going to be capitalized. So the M is the SI abbreviation for omega, indicating millions or 6 zeros. Hertz is the SI unit abbreviation for hertz, or cycles per second. And this one, I would say that you just, out of all the answers they give you, I would just commit it to memory. I think when you see it enough times, you get used to how it's spelled. All right. If it was gigahertz, it would be a capital G. If it was kilohertz, I think kilohertz, I've seen that one with capital K and a lowercase k. I tend to use a uppercase K. To be really honest with you, this is kind of a stupid question because at the end of the day, I don't think anybody really gives a rat's tail of, I think everybody gets the idea, even if you used all lowercase, right? I mean, there's nothing else in ham radio that's lowercase MHZ versus uppercase. So it's kind of silly, but what formula is used to calculate current in a circuit? Okay, this is the one where resistance comes into play. Okay, and it's going to use the other. It's going to use the EIR one, not the PIE. And the best way is, you know that all these have resistance in them, right? So we just have to look at which one makes sense. So if I wanted to find current, I know by covering current, which is the I, this will be one right here, there's only one answer, and that is volts divided by ohms. We go back, volts divided by resistance, or ohms. So even these worded questions, if you write out these diagrams ahead of time, and it's the same method that we use to find wattage. Okay, so we're going to go through a couple of these questions. And I like to think it's a gimme, Richard, but there's some people that can figure this out. We got a couple people in this class that I know that are almost electricians. They wouldn't even think twice about this. And there's some of you that if you didn't have this pi, these little circles to draw, you would be lost. I would be lost because I'm not an electrician. So yeah, point is, give me for some help for others, I guess. So if I wanted to find the volts, again, volts equals, so you would put your finger over the voltage. You want to find out what equation out of these answers gives you voltage. Well, if you cover up the E, it's amps times resistance, or amps times ohms. Okay, so current divided by resistance. Yeah. I got you, Richard. I got you. Like I said, though, you saw that question. It said lowercase m, uppercase H, and Z. At the end of the day, who gives a rat's ass, right? I mean, it's MHZ. It's megahertz. There's nothing else to get it confused by. So all right. So if we wanted to find the resistance, we put our thumb over the R, and we would get the volts divided by the amps. So let's do a couple of these. What is the resistance of a circuit in which the current is 3 amps, flows through a resistor connected to 90 volts? So they gave us 3 and 90, right? We want to find the resistance. So it'd be E divided by I. For E, they gave us 90 volts. For I, the amperage, they gave us 3 amps. Divide 90 by 3, we get 30 ohms. The omega sign is that one I think most people get. The omega sign is the sign for amps. I'm sorry, for ohms. And it looks like an O. So go to the next one. What is the resistance in a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? So again, they want you to find the resistance. And they give us 12 volts and 1.5 amps. Divide 12 by 1.5, we get 8 ohms. And that's how we arrived at that answer of 8 ohms. Whoops, sorry. What is the resistance of a circuit that draws 4 amps from a 12-volt source? So it appears right here, 3 questions so far have used the same. I will tell you that you typically aren't going to get 3 questions in the same. You're not going to get 3 questions that use just this one. It's typically going to be maybe 2 of one, 1 of another, or 1 of each. So they give you 12 volts and 4 amps. 12 divided by 4 is 3 ohms. What is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? So what we're trying to find now is the current, which is I, right? They give us the E and they give us the R. So we cover the I. And for E, volts, they give us 120 volts. For R, ohms, they give us 80 ohms. So 120 divided by 80 is 1.5 amps. Now remember, any one of these questions are going to be on the test. Now, also remember, these 4 answers are going to be on these 4 possibilities are going to be on the test. Okay? It's not that they give you the right one and then pick 3 others and these are random. This is exactly as you're going to see it on the test, except the right answer 1.5 amps may be letter A. But you get the idea. These are going to be the 4 choices they give you in any order to this question. So you're not going to get 3 mysteries and these will change, but the constant is this 1.5 amps. These 4 is exactly what you're going to see for this question if it's on your test. So just keep that in mind. So at worst, if you don't remember or you have a little bit of friction with it, the safest fallback is commit to memory. Okay, so what is the current through a 100 ohm resistor connected across 200 volts? So again, we're solving for I again. And they gave us 200 volts and they gave us 100 ohms. And if you look at this, 100, 200, so you're looking at either knowing that you're either dividing or you're subtracting. I don't even have to look at the pi because I can see either my answer is going to be, well, if I were to multiply, it'd be 20,000 or it would be 2. So I can automatically take 2 of these out. What is the current through a 24 ohm resistor connected across 240 volts? Remember, 240 volts is well, could be a voltage in your house. I have a hot tub that can run on 240. My dryer's 240. My stove is 240. And those are there are only 3 things, I think. The hot water heater, I think, is 240. Everything else is 110. So what is the current through a 24 ohm resistor connected across 240 volts? Well, again, I know that I can sit here and look at that without even looking at the chart. I know that either I'm going to multiply these 2 numbers or I'm going to divide them. Well, if I multiply these 2, the answer isn't even here. So the only other choice is to divide, and I get up 10. So you really don't need, if you really think about it and you just look at the question and you just stop for a second and read it, it's really kind of simple. You really don't even need to draw the circles and the pies. You know what I mean? But that's your choice. I mean, but when I look at this, I know that there's only one, either multiplying or dividing these two numbers that they give me. It's only two choices I've got. All the possible answers are all amps. So again, they give us 240 volts and they gave us 24 ohms. It's pretty simple, 10 amps. What is the voltage across a 2 ohm resistor if the current is 0.5 amps? So again, I can look at this and I'm either going to divide or I'm going to multiply. Only two choices. There's no addition, there's no subtraction. So I'm looking for voltage. They give me 2 ohms and 0.5 amps. So I have to divide my amps by my ohms. 0.5 amps divided by 2 ohms, I get 1 volt. What is the voltage across a 10 ohm resistor if a current of 1 amp flows through it? Wow. No subtraction, no addition. There's really only one answer. Right? I mean, I don't even have to look at the pie chart. When I took the technician, I did learn about this when I was taking the technician test. I did learn this formula, and it greatly helped me. There was a lot of things I didn't know when I took my technician that I do now that I'm teaching you, but this was one that I had been shown by somebody. So again, 1 amp times 10 ohms, 10 volts. I mean, even if it was, we went back here and it was 10 divided by 1, it would still be 10. 10 times 1, 10. So, what is the voltage across a 10 ohm resistor with a current of 2 amps? So, this is either going to be 5 or it's got to be 20, right? Multiply or subtraction. Either 5 volts or 20 volts. Well, there is no 5 volts as an answer. So I know it's got to be the other one. It's got to be 20 volts. But it's because we're going to use our diagram anyways. And 2 amps times 10 ohms, E equals I times R. So volts is going to equal 20 volts. What happens to current at the junction of two components in series? Now, I always get the series and parallel to this day. I always get it confused. I put a new system in my new car, sound system, and the speakers. I had to sit there and literally, I had to write it down on a piece of paper. So don't think, again, and I'm an extra class, so that tells you, like, I don't have it committed to memory. I still got to write it down. So, but it's unchanged, okay? The current is determined by the total resistance through the whole series. So the current at the junction is unchanged. So when you watch this on the replay, you'll see this animation, but when I have the PDF, you don't quite see the animation as much. And I tell you that the best way is, if somebody has a better way, if Eddie was in here, or even if Carol was in here, but I don't have a way to tell you how to memorize series and parallel as easily. I don't have a surefire way to tell you. It's something you just got to kind of commit. What happens to current at the junction of two components in parallel? So it divides between them dependent on the value of the components. So Notice that across the components in parallel, the current is 85 milliamps. Is divided between the components based on the value of the components. So all these added up, 50, 25, and 10 gives you the 85. In this case, the components are resistors, and their values are resistance in ohms. The dots are moving faster through the 100 ohm resistor than they are through the 500 ohm resistor. You see that? So there you go. They're moving a lot faster through this. You remember the resistor is the squiggly lines. It's moving much faster through the 100 ohm resistor than the 500 ohm resistor. 500 ohms is higher resistant. It's going to have a higher resistance. That's right. Least amount of impedance, least amount of resistance, least amount of opposition. You have the most flow. So what is the voltage across each of two components in series with a voltage source? So it's determined by the type and the value of the components. The component in the series doesn't change, but the voltage across each of the two components does change. So it is determined by the type and value of the components, in this case, the resistance of the resistors. I could get into the much deeper math, and we could, I think that might confuse you a little bit more. But so it is determined by the type and the value of the components, which makes sense, okay? What is the voltage across each of two components in parallel with the voltage source? So we said earlier that the voltage doesn't change. Here, the voltage across each of these does change. If we go back to this one, so you're asking, Jason, so in parallel, does the speed change as it goes through the different resistors? Yes. The lower rated resistors, there's not as much resisting the flow, so more power is going to go through it. More of a current is going to go through it. The 500, if you see here on the far right, this is a 500 ohm resistor. It's resisting, has the same amount of power coming through it. I'm sorry, same current coming through it until it hits these resistors. And then on the other side of the resistors, you end up with less current because there's more resistance holding back the current and not letting as much through. Hey, Dean, how are you, man? So look at these in the replay. Look at these and try to make some sense on your own with it. Offhand, I can give you a diagram. I just don't have the words to be able to describe it. I understand it, but I'm not able to put it in words. So in series, the current is the same through the entire loop, so the speed is the same through all components. Okay, so let's go ahead and jump over onto we are going to go, hold on, We got to go into section 6. Okay. Okay, so section 6, we start getting into electrical components. Okay, there's 4 exam questions. Yeah, guys, if you want, we're all in this together. I can't promise to know everything, and when I do, sometimes I don't know how to put it in words that is easily understood. So if you guys can, if there's a concept you get, spit it out, man, share it, and make it simple for others. I know when I take time and I look at those diagrams, it makes sense to me. And I could keep talking about it, but I might just end up confusing you more. So, what electrical component opposes the flow of current? Okay, well, remember that word opposes the flow. The only thing in here that opposes or resists would be a resistor. So it may help you to remember resistor as a synonym for oppose, as in oppose the flow of water. Now we're going to start dealing with the schematic symbols. But these are really cool because I think that you can understand these when you really look at them. So when you look at a schematic chart, hopefully on the other end of this journey, you'll look at a schematic chart and you'll think for a second when you look at them and we study them together, they kind of look like what they say they are. Once I show you a picture of one. So a resistor, basically, it has stripes that are rated. You don't need to know about the stripes. They're not going to ask you colors and all that. But when you see a resistor, they have several different stripes on them in different colors. They mean something. It gives you a rating for that. How many farads it is, microfarads. One of the biggest, most common resistors that you see in everyday life that's sitting right in front of your face is not volume knobs. Anything with a volume knob or a dial, temperature, those are what we call variable resistors. And they're variable because the value rating of them, it varies according to what you set them to. And this right here, this right here is what we call potentiometer or a pot. You see these every day because these are behind, this part is behind the panel, and this part usually has a nice little beautiful plastic knob on it that means something to you, that has a little painted stripe on it. So you see these every day. Some of these push in and pull out, but for the most part, you see these each and every day. All of us deal with some kind of dial, our thermostat, our ovens, when we go set the temperature and we have to dial the temperature up. It seems like these days we are getting a little bit farther away from knobs, dials. And the reason why is because they tend to get dirty and they end up getting scratchy. So in this digital age, we've gone to, touch sensors and things like that. So I just want to show you that that's what typically a resistor most commonly looks like. And the other picture here is the other resistors that you would see on a board, a circuit board. Okay. But remember, this is a variable resistor, and we're gonna get into that more here. So what type of component is often used as an adjustable volume control? And we just said it's a potentiometer. A lot of times they just call it a pot. Okay. So I've been a musician my whole life, played guitar. So my guitars have dials on the front of them, so do the amplifiers. And it's nothing that you go to turn the volume or the tone and you hear this scratching as you turn it. You take it to a technician, he goes, your pots were dirty. And all he does is he sprays contact cleaner. He gets up in here and this is a pot. he goes in here and he sprays contact cleaner inside here, because inside of here there is a wiper blade, and there's a contact inside here, and depending on where that wiper blade comes in contact, it swipes around in circles, and the higher it goes, the least amount of flow is able to go across that contact, so the resistance increases. So when you look at a schematic, the telltale sign of a variable, anything that's variable, is it will have the symbol for that item or for that component, and then it will have an arrow on the output side of it. It will have an arrow that points back into it. And that's your telltale sign that that it is capable of accepting a variable input from a user of some sort. Okay, we're going to see this in a schematic. There's other things that are variable as well in nature, but this is one of the biggest ones, is a potentiometer or a pot. What electrical parameter is controlled by a potentiometer? Okay, so potentiometers are rated in ohms. So most of the time, these are going to be 250 ohms or 500. They're 500K or 250K is what they're rated at. That doesn't really mean anything. That's not important. Just wanted to add that to you. But and all a potentiometer does is when it measures the resistance, is again, there's a blade, there's a wiper that is attached to this shaft here, and as you turn this, that shaft goes around the circumference of this pot, and inside of here, on the top of it or on the bottom, usually on the top here, there is a contact strip that goes all the way around. So one of these is going to be the input, one's going to be the output, and one's going to be the ground. So the best way that I remember this is I look at this and I see so when I see potentiometer, I think potential. Okay. And the only thing that keeps me from reaching my potential is resistance. Stinking thinking, bad thoughts, discouragement, that is resisting my success in achieving that goal, that potential goal. That's how I remember it. So again, it goes back to the resistors. Some of these pictures I'll use over and over again, but repetition helps. You don't need to know about the different color stripes on the test, but just know that the stripes usually indicate a rating. Now, somebody that's into electrical work can look at this, and most of your electrical guys, electronics guys, they have a little chart that they look at. They don't even memorize these. Okay. What electrical component stores energy in an electric field? Now, this is really important because there are two components that store energy. Okay. One of them stores it in an electrical field. The other stores it in a magnetic field. The way that I remember this is electrical. Usually I want to know the capacity. So if I have a fuse, well, what's the capacity? How much amps does this fuse take before it blows? What's the capacity? The maximum number of amps. Or a resistor, the ohms. I think of capacity. When I think of magnets, I don't think of capacity. There are two questions on the pool that are very similar. One asks about components storing energy in an electric field. The other is a magnetic field. Okay. The electric field is a capacitor, and it consists of two conductors separated by an insulator. So capacitors store energy in an electric field. One way you can remember this is the acronym MICE. Mice, magnetic field inductor, capacitor electric field. If that helps you any remembering mice. This is that should be gray right there. The reason why it's white is because usually what it's signifying here, trying to signify, is an insulator. Air is an insulator. Okay. Now you remember the variable capacitor has an arrow. Now you could say that the arrow could be on the end here and come back into it. In this particular case for the capacitor, they've put an arrow through it. A variable capacitor would be a potentiometer, right? A fixed capacitor. So this would be a variable, and this would be a fixed. One of these would be a fixed. This would be variable. What type of electrical component consists of two or more conductive surfaces separated by an insulator? Well, if you can remember what the schematic for a capacitor looks like, it's usually two plates. And it doesn't always that. So when we saw this other one, you saw the fixed capacitor, and usually there's stripes painted on this. Whoops, hold on here. So you might have green painted on it. Then you might have let's see. You may have red painted on this. Then you may have blue painted, and you remember, and they all mean something, and it'll tell you the rating of it. Well, inside of that is what this looks like. Okay, there's usually a metal foil, and there's something in between it. Usually, it can be paper, it can be a coated paper that has a special coating on it. It could be air. It could be anything that separates these two layers from touching each other, and it's just rolled up, and then it has a polymer coating on the outside to protect it from the elements and from moisture. So you have a capacitor. You have an air. This one right here. Let me get this one right here. Oh, dang it! Let me get a bigger. There we go. This right here, when we were talking about tuners, you remember the ATU when we were looking at where the SWR meter goes, and we saw that component called an ATU, an automatic tuning unit. That's what it is. This is what it looks like on the inside. That's just an air variable capacitor. But most of us have seen these pictures. We've seen these at some point in our life. If you open up anything and you see a circuit board, you're going to see these sticking up. Okay. So inside of these, I gave you a little of a diagram here. You see these two plates here. One is positive charge, one is negative charge. And in between is the insulator. And depending on the size of the plate and the thickness of the insulator, together contributes to what the value rating of the capacitor is. So hopefully I'm hoping that if I give you pictures and show you what they look like instead of just talking about them, it gives you some kind of context. And they come in all different types of shapes. But up here is that, now that you've seen these two plates, you see the plates here. If we go back to this one here, and you've got metal foil, which is the green one, and the insulating material, which is the gray, it kind of makes sense, right? I mean, I think the capacitor schematic symbol looks like what it is. two conductive plates with an insulator separating them. What type of electrical component stores energy in a magnetic field? Okay, so remember, two components store energy. The only difference is electrical capacity, capacitor, magnetic field, inductor. The way that I remember magnetic is everybody here maybe has heard of an induction oven. So it's one of those type of hot plates where when you put a pan on it, it heats up like instantly. But then when you take the pan off, you can put your hand on the burner and it's cool to the touch. Okay. Well, inside of that hot plate are magnets, and those magnets are reacting to the compounds of the metal. You can't use just any pot on an induction stove. It has to be a metal that interacts with the magnets that are inside of that hot plate. So that's how I remember induction oven. Inductor is that I know that it's capacitors that are moving the electrons across the surface between the pan and the magnet, and that's what's creating the heat. And that's just something I know. But so there are two questions again are very similar. One is about storing energy in an electric field. The other is a magnetic field. The magnetic field is an inductor. It usually consists of a coil of wire, and this is the symbol. It looks like a coil of wire. Now I'm going to show you what one looks like. Ding! Look at the schematic up here in the upper right-hand corner. Is that not a symbolic of what an inductor looks like in real life? It's just coiled wire. So I have an antenna that I use. It's called an end-fed half wave. End-fed half wave. Put it in chat. End-fed half wave antenna. And all it is one wire. There's a little box. It's a little project box that I buy off of eBay or Amazon. And I put one of these in it. And in fact, highlighter. This one right here looks a lot like what I use, this particular one. It's very reminiscent of it. And there can be a bunch of different, so an inductor, if you ever had the experiment in school, you remember you took the nail and you wrapped copper wire around it? You were creating an inductor. So what electrical component usually is constructed of a coil of wire? It's an inductor. Here's some more inductors. So the characteristics of an inductor may vary drastically depending on whether or not the wire has a ferrite core inside. So ferrite is just powdered iron. It's iron ore that has been ground down to a powder and then bonded back together to make a magnet. So all these little metal rings that are inside of here, so this little piece right here, that's just a ferrite material. This one right here, ferrite material. Not all inductors have ferrite material in them, that powdered iron. Not all of them. Here's a ferrite rod. Here's a ferrite ring. Sometimes you've heard of a term, maybe it's called a toroid. And that's what these are. They're called toroids. That's not important. Just giving you a little bit of information, just a little side note. But all these here create an inductor. But as well as look at these type right here. Okay. Let's see if I get all the, okay. So you've got these are different as well. Now it's real easy when you see these upper ones here. These particular ones, right. These right here, a lot of times these can be confused for transformers, and when you see a picture of a transformer, you'll know why. But there is quite a bit of difference. When I show you a transformer coming up, it'll make a little bit of a difference to you, because a transformer, the wire's wrapped around and there's air in between. This one, the wire's in the middle and it's wrapped. It has a ferrite material around it. I'm getting a little bit more confused. So it goes back to this is how electromagnetic magnets are made, such as those in old school electronics equipment. So if you, again, in science experiment, if you ever wrapped insulated wire around a nail and then you turn it into a magnet by putting a charge to the wire, you were creating an inductor. What electrical component is used to connect or disconnect electrical components? So it'd be a switch, right? We're going to answer this one and then we're going to take a little break. So it would be a switch. What electrical components are used to connect or disconnect electrical circuits? Well, it kind of really makes sense. I mean, when you want to turn something on or off or connect power to something, you usually have a switch in line somewhere to turn that power on. So possibly the most common example is the light switch in your house. When it's on, it connects the electrical circuit that the light in your room is on. When you turn it off, it disconnects the circuit. So there are so many different types of switches, but they all still do the same thing. They connect and disconnect. Okay. So a magnetron is usually a high-powered vacuum tube that generates microwaves. So you would find that in your microwave, magnetron. Inside your microwave, a lot of people think there's radiation in them. Not as much anymore. The old school ones were. Today, not so much. So a thermistor is a type of resistor whose resistance varies according to the temperature. So you would see a lot of those in like thermostats and big industrial thermostats. You would see thermistors. Even in your house, in your thermostat on the wall, you would have a thermistor. Okay, depending on what the temperature of the room is, would provide more resistance. If you ever opened up the cover of an old school thermostat on your wall, it's just a flat copper ribbon that is wrapped, is coiled up, and depending on the temperature, that coil contracts and expands, and there's a little ball of mercury on the end, and the mercury is what, when that strip expands so much, there's a contact that the mercury makes. So if you've ever opened up the cover of an old school thermostat, if you have one, take off the cover, just gently take off the front cover and look inside of it. I have an Ecobee thermostat, so I have one of these smart faint angle ones I can use on I can control from my, from the internet. So Mr. OPSEC Gray Man here has an internet controlled thermostat, I know. So anyways, a switch is an electrical component that is used to connect or disconnect electrical circuits. So I gave you a schematic here, and we're going to get into what these mean. Single pole, single throw, single pole, double throw. That's just a schematic. And when you see, it kind of makes sense. When you flip this, when you have this toggle switch or this slide switch or this rocker switch, all it's doing is on the inside. When you flip it one way, there's a contact that comes off of one side of one of these leads and makes contact with the other side. So it either grounds out or it completes the circuit. So this arm would come close, and when it does, it would bridge these two contacts and circuit would flow through it. Okay. And again, we're going to get into the whole SPST and SPDT. They're really not that hard. I just wanted to throw that symbol at you so you could see it really quick. So let's go ahead. Let's take a 5-minute break. Go use the bathroom. Get something to drink, and we'll be back here and let's say 9:15. I'm staying here. Anybody got questions? If you don't have to use the bathroom or anything, you want to ask me a question, something we covered, I can go back real quick in the 5 minutes that people are. Anybody. You guys can ask me any questions. Let's see here. Basic repeaters. I'm going to share the supplemental test graphics now. Supplemental test graphics. You can download it right here in the chat window. I think it's, for me, it's the third icon down from the bottom. File sharing. And I think that you will find a lot of these diagrams and things are on that supplemental test graphics. No question, but I connected to a GMRS repeater in Charlotte today. So you bought a license. Yeah, what is the license? Is it like $60? 60? You don't take a test or anything. You just have to pay the government to be able to use the GMRS frequencies. It's kind of silly, but it is what it is. Don, will this be repeated? $70 for 10 years. Wow, it went up. I thought it might have always been 70. I thought it was 60 at one time, but nevertheless, the whole extended family is included. Wow. I think it's silly when you think about that, though. How do they enforce that? How do they accept what everybody in your family uses the same call sign that they give you? So Don, you asked, will this be repeated? What do you mean by that? I'm not. Will this whole class be repeated again? Not sure about call sign. Then how? So, and I'm not. You're teaching me here for a second. I really don't have a GMRS license. How do you identify with each other? For GMRS, I mean, there's like, I want to say there's 6 or 7 possible frequencies. So how do you identify yourself then? I mean, I wonder if they're going to send you a call sign. So Don, you're asking, is this will this class be repeated? Well, no, and the reason why is because it's being recorded. If you go to www.preppernet.com/tech and you register for it's PrepperNet website. They have a free basic membership. Premium membership, I think, is like $40, and the thing is just growing by the day. But basic will get you access to all the PowerPoints, all the class material. There's even the videos. We're being recorded right now, and you'll be able to hear. You'll hear me call out your name in the video, just first names only. But nobody can see the chat window though. In the replay, you also get that email at the end giving you a replay video that you can watch. I've been told that the replay video that you're given, you're not able to fast forward or rewind, but on the PrepperNet site, you're able to queue up. You're able to go forward and backward, I think, to see the video and stop and stuff like that. So yeah, so Beth, I don't know if you knew what that website was, but I'm gonna put it up here anyways. It's pretty easy. Whoops, sorry. And I think if you go there, and if you're registered as the trustee, I guess maybe you can search by your name and get that call sign. But when you reached out, you said you looked at a GMRS repeater. You connected to a GMRS repeater in Charlotte today. Does that mean you just listened? You were able to listen on the repeater. You didn't transmit? Because I imagine if you don't know what your call sign is, I'm not sure how you. Okay, but I'm already famous. Okay, famous. You're already famous. Don, yeah. So how'd you identify yourself, Beth? And again, I'm not, you're teaching me here. Honestly, I just have never played with the GMRS frequencies. It's I think it's part 70 or part 90 or something. It's not part 97, I don't think. Huh. And you just used your neck. Did you just use your name, or? I guess that's what I was wondering, that's all. I said CQ and said I was new. They used their call signs. But you weren't able to use yours because you don't know yours yet. I guess it'll appear in the FCC database soon. Yeah, typically you're not supposed to transmit until you get the call sign, but who cares? I mean, honestly, really, I know I'm probably going to eat crap for some of the things I say in this class. But I haven't given out my call sign in this class for a reason, and Natty Green's not my real name, so the FCC can, well, they can suck my ass. Anyways, I said it. So, yeah, you're not supposed to transmit, but you do, and nobody's going to come knock on your door, but it's just discouraged. So the reason why I don't give my call sign out is because I have over 300 people attending this class from about 4 different groups, and I can't guarantee who's given the class link to other people. And if you have my call sign, you would be able to run me in the database, get my address and my real name, and I don't really. If somebody out there, says that I'm not teaching the class correctly or I'm giving wrong information, well, you just tell me when you're giving your class, and I'll be glad to attend and learn something that that I don't. So I just say that. My objective is to get you to pass this test. That's it. If you're like me, you can you can tell me and I might remember, but if you show me, I will never forget. Everything I know about radio I did by learning. A test only gave me the privileges to be able to learn from doing. So yeah, so there's some people in this class that know there are some people that attend this class, they know my real name and they know me, and it's all good. If we were on a personal basis, I have no problem saying it to other people, but this is being recorded for prosperity for the next 4 years. So it is what it is. If anybody has a problem, they can find Natty Green on Facebook and tell me how much you love me or how stupid I am. I really don't care. So I say that because there's people in this hobby that in ham radio, they're purists. And like any hobby, you've seen it in shooting, or if you guys shoot and you're learning to shoot, or you even see it in hunting, or any hobby that you're in, you get those that are mentors and you get those that are discouragers. They bring nothing to the table to help others. Their sole purpose of existence is to tear people down. It's in everything you do. Ham radio is no different. But I will say that a majority of the folks overwhelming majority of folks are there to answer your questions and help you. But there are those segment of folks that think that you need to be an electronics guru and need to know how to build a radio from the chassis up before you can get your technician license, and it's just kind of silly. Those people usually don't have a life. So, all right, let's get back into it. But yeah, Richard, OPSEC, that I just kind of learned to play, just be a gray man and just kind of keep it simple and stupid, and you know, I'm doing my part to share the wealth and knowledge a little bit, and you know, who I am and where I live and all that isn't important, but you'd be surprised how many people keep an emphasis on it. So anyways, so what electrical component is used to protect other circuit components from current overloads? Honestly, this has got to be a gimme. I'm sorry, but it's got to be a gimme. Think about your house, your car, anything that is an electrical circuit. What do you put in place to ensure that it doesn't overload, overheat, and catch on fire? A fuse. These are different fuses. So on the left side, this is a type of fuse that you will usually see in the back of a radio. It usually just has a spindle. You unscrew it, and this second one goes up inside here, and it just completes the circuit. And depending on what this fuse is rated at, how many amps it's rated at, and when it exceeds those amps, this little wire here will break, and it will break the circuit. It'll keep the circuit from flowing from point A to point B. Same thing with these auto fuses. We've all seen them, right? Well, they could say circuit breaker. Does it say circuit breaker? No. Yes. When you think about manufacturing, circuit breakers aren't cheap compared to just a fuse holder. So it's nickel and dimes. It's just like, why didn't your car have circuit breakers, right? Just cheaper. We all seen these ones, these blade types on the right-hand side, and you look in the little window here and you see the little wires. You know, this one's got it too. Let me go and highlight. So this one has a little wire right there. This one has its wire right there. And depending on how thick this wire is, you see how this one right here is really thick compared to this one. You can barely see. It's just really thin. And this one's thin as well. So depending on how thick that arch is there, that's what really is rate. It's just like this one right here. This wire in the middle is what really rates the fuse. The thicker the wire, the more load it's able to take before it snaps. So, which of the following battery types is rechargeable? Well, all these are. So we've heard of nickel metal hydride. Those have kind of, nickel metal hydride has kind of gone away because nickel metal hydride tended to have a memory. Somebody correct me if I'm wrong, but lithium ion doesn't have a memory. In other words, nickel metal hydride, you had to be careful when you charged it. You had to charge it all the way up, and you had to drain it all the way down, then charge it back up. And if you just charge it all the way up and use just a little bit and charge it up and use it a little bit and charge it up, it gains a memory to it and only thinks that it has the batteries of a smaller capacity. The problem, though, is that lithium-ion batteries are susceptible to cold weather more. They don't operate quite as well in extreme weather. Heat usually isn't the problem with batteries. It's usually cold. And I think we've all experienced that in the wintertime. You know, your car doesn't want to start. Summertime, when do you run into the most starting issues with your car? In the wintertime, right? So, lithium ion batteries don't have a memory to them. So so if you buy a Baofeng, if you ever seen, as soon as you get it, you can turn it on. It's got about a half a charge in it. And you're not going to ruin it if it's half a charge and you run it down all the way. However, I would say also that lithium ion batteries do not last as long as nickel metal hydride batteries do. They only got, I believe that the lithium ion batteries only have but so many rechargeable cycles in them before they're just depleted. Nickel metal hydride, I think, nothing is infinite, nothing lasts forever, but I think nickel metal hydride tends to accept more charging cycles than lithium ion. Lead acid gel cell, so we usually call those AGM, acid gel mat. So inside of a battery, you have a series of plates or mats or cells. All three of them mean the same thing. Each plate is a cell or a mat. Okay, so all three of these could be recharged. So this top one here, this you've seen with your Baofeng, that is a lithium ion battery. You can buy these days your AAAs, AA's, 9 volts. You can buy those in lithium ion too. It took a while for them to do it, but however, your carbon zinc batteries, like your Evereadys, Duracells, Energizers, those are not rechargeable. Some people would argue with me that you can recharge them to an extent. And I certainly have recharged. I have put a charge onto a Duracell battery and energized it a little bit, but you don't really truly recharge it all the way. Okay. So which of the following battery types is not rechargeable? Okay. So again, lead acid batteries, think of like lead acid batteries would be your car battery, right? There's acid inside of it. They tend to let off gases. You have to keep lead acid batteries. Typically, you have to keep in a ventilated area so they can breathe. But carbon zinc batteries are not rechargeable. There's a quick way that you can remember this is you can't zap a carbon zinc. CZ. Can't zap a carbon zinc battery with an electric charge and recharge it. Okay, so the chemical reactions that occur inside of a carbon zinc battery are not reversible. The other types of batteries, they are. The type of chemicals and the cell inside of them allow them to for the charge to vary, to be recharged into depleted, recharged, depleted. The type of acid, the type of chemicals they use inside of carbon zinc batteries, they only have a certain amount of life to them, and eventually the battery just becomes inert. The chemicals inside of it just lose their capability of holding a charge slowly but surely, and they just become an inert. And that's why a lot of times those type of batteries also, carbon zinc batteries, will leak a lot more than rechargeable batteries, I have found. That's not always the case. You get cheap rechargeable batteries, or cheap is cheap. So, what class of electronic components uses a voltage or current signal to control current flow? Okay, the best way that I remember this is, I think when I think of transistors, I think of transition. Okay, transition. And typically in current flow, you have a current that is transitioning through the line. Okay, it's leaving its port of origin like a battery, and it's transitioning through the line to either a light bulb or to a component to charge it or something. And that's how I remember transistors, as transition. Transistor is an electronic switch that enables the current flow between two terminals if a current is present on a third. Okay, so think of it as a push button switch. You push the button, so transistor typically is going to have 3 leads to it. Okay. And this is going to be on the test, but you have a base, an emitter, and a collector. Okay, a BEC. Base, an emitter, and a collector. It is on the test. Pretty simple to remember when I show you. However, this is what a transistor looks like. Let me get me a laser pointer. Okay. So, before I even went to it, now I got a little trick for you here, just like a tube. So, in your test, you're going to have something that's called a PNP and an NPN. Okay? And when you look at the schematic chart, I want you to think of this as a toilet. That's right, I said toilet. This is your lid. The arrow points in when you can pee into the pot. Arrow pointing in, you can pee into the pot. When the arrow points out of it, no pee in the pot. So no pee in it or pee in the pot. So the arrow points in, pee in. Arrow points out, no pee. That sounds funny, but now that I said that, you're never going to look at a schematic for a transistor again the same. There's your toilet. There's the lid. It's opened up. The lid is open. And that's how you can tell the difference between what a PNP is and what an NPN is. I'm waiting for the comments for somebody to come across. Really? We really went there? Yes, I used the toilet. So it can be used as an electronic switch or an amplifier. Okay? And it's comprised of 3 layers of semiconductor. So generally it's going to have 3 electrodes. Remember I told you the emitter, the base, and the collector. I said generally has 3 electrodes. There is something called a FET. So when there's a circuit called MOSFET, and in a MOSFET circuit or a FET circuit, field effect transistor, the way I remember that is I remember there's a gate to the field, okay? And usually I close the gate to the field when I need it to drain. So a FET circuit is going to have a source, a drain, and a gate. A PNP or an NPN circuit is going to have emitter, base, and collector. Might be a test question we will now know. I know, it's the toilet, the lid. You can pee in the pot. Arrow goes out. No pee in the pot. A transistor is a semiconductor, which is a fundamental component in almost all electronic devices. So transistors, with the advent of transistors, it has been considered to be the greatest significant achievement and invention when it comes to electronics in the 20th century. Because of transistors is how we ended up with semiconductors. We ended up with CPU chips. Ultimately, because of transistors, you have your cell phone. You have this computer that you're listening to me on right now. It really comes down to the invention of transistors that was enabled that. So remember, transistors have many uses. They can be used as a switch. They can control, they can regulate the transition of current or voltage. They can also amplify a signal. That's right, NPN, not pointing in, not pouring in the pot, not pouring in, or, yeah. I just said, yeah, I said no pee in, and I used a toilet because it's like, you're just not going to forget that now because there's nothing else on the test that I talked about a toilet. It's like, yeah. And it can be kind of confusing. So I've always stuck with that. And for whatever reason, people, it just sticks. They just remember toilet. So, sorry, got you. What a weird mnemonic. So, Which of the following components, electronic components, allows current to flow in only one direction? Okay. So a fuse, we know a fuse isn't the answer, right? Because a fuse's job is just to make sure a circuit doesn't overload. A resistor, all a resistor is going to do is what it says. It's going to oppose, it's going to resist a flow of current through it. So if you have a 200 amp line that you want to have 10 amps, you would use a resistor to help control that flow. So you're only left with two other answers. Okay, so let's talk about, it's a diode, and we're going to talk about why it's a diode. So a diode is an electronic component that only allows current to flow in one direction. The most commonly known type of diode these days is an LED. LEDs are everywhere now, right? I mean, now, you know, cars, a pretty economical car these days, low-end car, is going to be using LEDs for headlights and things like that. It used to be just, what, 4 or 5 years ago, you only got LED brake lights on your high-end, highest trim levels. Now, man, they're on every trim level. And the reason why is LEDs require so little power to run them. So little power to run them. And also, LEDs are susceptible. They can take vibration. They can take moisture better. And because of that, and they don't require as much power, once you use an LED bulb, you're not going to be replacing it probably for the life of the component. It's going to be a long time. If you have LED brake lights on your car, every once in a while you'll get a malfunctioning one, but it's nothing to find cars out there that are 10 years old with LEDs on them. Nothing at all, still original. But chances are, if it was a light bulb, you've changed it in 10 years. So a resistor allows current to flow in both directions, but resists the flow of current. The fuse is something that allows the current to flow in either direction, but when too much current flows across it, it blows the fuse. And a driven element is part of an antenna that a transmitter causes to emit RF energy. So I'm giving you what the other three were, why they can't be the answer. Okay? So a diode, look at the schematic for it. Okay? Now it tells you that it's only going in one direction. Well, here's an arrow to tell you that goes in one direction. The reason why you have this block on one side of it is because look at the diodes here. You see that stripe? That tells you what side it is. That stripe is also happens to be the negative side. It only goes in one side, positive and negative. And the reason why this wall, what you want to call it, whatever, is that signifies the negative ends. And when you're looking at a diode, usually the negative end is going to have a stripe on that end. So again, a diode is a one-way valve, and it gives you the arrow for it. Okay, it's used in rectifiers. Mostly, they're going to be made of silver. That's probably the most common substance in them. And there's different types. I wouldn't worry about the different types. The PM diodes, Schottky and PM diode. When you go for an extra exam, Schottky is a big part of the exam. You deal a lot with Schottky and PM diodes. So electrodes are called anode and cathode, with the cathode indicating a stripe. Okay. The way that you can remember that cathode, I've given a kind of a pictorial of all the different types of diodes that you can have. Remember, you have the LED is the most common that you deal with every day. And they just come in all different shapes and sizes. And so when you're looking at a circuit board, a lot of times, you know, a transistor can look a lot like a diode. One of the giveaways is how many leads does it have? A diode would have two, an anode, a cathode. And you remember a transistor has a base, an emitter, and a collector, or has a gate, a drain, and a source. Which of these components can be used as an electronic switch or amplifier? So really, again, when I think of transistor, every time I see the word transistor, I automatically group it with transition. Okay, so a transistor, something is going to happen to that current. Okay, it can either be turned off or on, or it can be amplified. Transistor has three elements. On the most common type of transistors, again, you have the base, the collector, and the emitter. Okay. Current applied to the base controls current flow between the collector and the emitter. So when we look at let's go back here again. We're going to go back a few. Here's your base. Okay. Here's your base. The emitter is the one with it tells you the direction. Okay. The emitter, so it depends on whether it's a PNP or an NPN, whether it's a positive or a negative. It gives it to you right here. That's not really that important to know the negative and positive and all that, but you want to try to remember a transistor, a collector, base, and emitter. You just want to kind of remember those three. You don't even see here where they telling you which one of these legs is which one's the collector, which one's the base and emitter. You don't even need to know that for the test. This is just information to hopefully give you substance that you can latch on to for memory. Okay, so let's go back up. So the other two answers they give you is they give you an oscillator. An oscillator is something that produces a signal. Okay. A potentiometer is a variable resistor, and the voltmeter is a tool that can be used to measure volts. That's kind of, a meter that measures volts. I mean, it's in the name. So none of these can be a switch of any kind. If any of these have the potential or have a possibility to be, if you want to blur the lines, a potentiometer may resemble somewhat of a switch behavior, but a potentiometer doesn't connect or disconnect a circuit. Okay, it doesn't bridge a circuit or break that connection. While specifics of how a bipolar junction transistor works is beyond the scope of this explanation, and it may be helpful to remember that nearly any time you hear the term semiconductor in casual electronic jargon, someone is talking about either a transistor specifically or about something made with many transistors, such as an integrated circuit or an IC is what it's called. Which of the following components can consist of 3 layers of semiconductor material? So 2 layers of semiconductor material with an insulator in between would be a capacitor. 3 layers would be a transistor. Okay, now remember, base, emitter, collector. Those are your 3 layers, semiconductor material. Bring back up this again. They each have 3 leads to them, every one of these examples. This one here looks like it has 2. I don't know why it's not showing you the 3rd one, but there's a 3rd one there. Which of the following electronic components can amplify a signal? So, again, I think transistor, I think transition. So a variable resistor is not going to amplify a signal. It's going to a resistor. It's going to reduce a signal, but it's not going to amplify it. Multi-cell battery just is providing the power. Okay. A transistor is a semiconductor device used to amplify and switch electronic signals and power. It is composed of a semiconductor material with at least 3 terminals for connection to an external circuit. A voltage or current is applied to one pair of the transistor's terminals. Okay. And so to the terminals changes the current flowing through another pair of terminals. So you remember you have the base. The base is always going to be consistent. It's really the switch is between the emitter and the collector. Because the controlled output power can be higher than the controlling power, the controlled power, the output, can be higher than the input power, a transistor can amplify a signal. How is the cathode lead of a semiconductor diode often marked on a package? Okay, so the cathode is the negative end, and it's going to have the stripe. And the way that I remember that is a striped cal. So here we go. The cathode is the negative end. We have one line, kind of represents the negative, and we have a stripe on that end. You can think of a striped cat. So striped cathode. Some people think of striped on a cathode side. This one doesn't work as much as a striped cat. A lot of people remember cathode as the striped cat. Your choice. I bet you that's some good chocolate milk that cow produces, don't it? Anyways, what does the abbreviation LED stand for? Okay. So we know what LED, in today's terms, LED doesn't elude anybody. Everybody knows what an LED is these days. Now you're left to buying the bulbs. I will tell you that in your house, especially with HF equipment, that those CFL bulbs, those compact fluorescent lights, they are the worst. They emit more RF interference, RFI. They are just awful. I know everywhere in my house I use LED bulbs. One, because I like to think it saves power, but I might argue on that one. But LED does not produce any interference. So, and out of all these, what does LED stand for? We know LED is a light, and there's only one of these that has light in the answer. Okay, and we know it's a diode. We talked about it being a diode. So it's a diode that emits light. Again, none of this is on the test. None of this, the answers here are on the test. But I just wanted to give you a breakdown of what it looks like inside. And usually this is sealed in. I mean, it's solid plastic around it. LEDs don't really produce a lot of heat. They do produce some heat, not nearly as much as a bulb with, I don't know what you want to call it, an incandescent bulb or a compact fluorescent bulb. I would say LED, for the amount of output light that you get in wattage, doesn't produce nearly as much heat. Wonderful EPA, I know. Well, you know, they thought they had us with the CFLs. And I will tell you that if you're using LED light bulbs in your house and you notice that either you, your spouse, or your kids tend to you are more susceptible to headaches, a lot of times it's going to be the LED bulbs. That's the only downside to LED bulbs. And that's because of the frequency that they emit. it messes with the connection between your eyes and your brain. And so if you're around LED bulbs for an extended period of time, some people can be susceptible to headaches. I think that same argument can be made for fluorescent bulbs as well. So at the end of the day, nothing beats those incandescent bulbs. But you know what's so funny is didn't the federal government ban those incandescent bulbs? Am I correct that they banned those? But you can go to Walmart now or Lowe's and you can still buy incandescent bulbs. So I don't know what that was all about. Why there was that cutoff where you weren't going to be able to get them anymore. We all went out and bought a crap load of them before CFL was all that we could have. And then when we found out that it takes just short of an EPA Superfund site to clean up a broken CFL bulb, they all of a sudden became attractive, and LED bulbs came down in price. I remember one LED bulb could cost you $15, $20, and now you can buy them for less than $1 a piece. So anyways, again, diode, same symbol as a diode, one direction, right? But this one has arrows that come off it. Now those arrows don't come back into the component like a variable inductor, variable resistor. They just go away from it. So that gives you an indication of light emitting away from the component. Lobbyist. So what does the abbreviation FET stand for? So field effect transistor. I don't know of a way that you can, there's some, I can remember the difference between, a gate, a drain, and a source versus a base, collector, and emitter, because I hunt, and because I hunt, I think, a gate is close to a field when it's flooded, so it needs to drain. So field drain or gate drain, that's just me. I think when I think of a field, I think of it needing to drain. So that's how I'm able to draw that correlation. So field effect transistor controls voltage and current like a regulator transistor, but can operate on a much smaller signal, which makes it ideal for radio receivers. It operates using an electric field to control the shape of the channel in the semiconductor material. And I don't really have, again, I don't have a way for you to remember that. So Richard says that I guess field effect transistors are highly receptible to electronic static discharge, ESD. I know that, capacitors, you have to be careful of capacitors, especially like in televisions. When you go to unplug a television, don't go open a television and think you can just throw a screwdriver inside there and start working. There are components inside of it that store energy that will cleanly knock you across the room if it doesn't kill you in the seat you're sitting in, because the stored energy and capacitors are in the back of the television. So, what are the names of two electrodes of a diode? So we have the anode and the cathode. And the way you can remember that out of all these, so the source and the drain. Source in the drain would be a FET, field effect transistor. Gate and a base. The problem with that is that one of these goes to these go to a transistor, right? Both B and D are parts of a transistor. And D would be, you have the base and you have the base of a normal transistor, and you have the gate of a field effect transistor. So anode and cathode. Electrodes are referred to as either anode or cathodes, regardless of whether they are on a diode or on another component. Current flows into an anode and out of the cathode. Cathode is negative ends and has the stripe. The schematic shows the line. You see the direction. So just by looking at a schematic, you can see the arrow with the line there. It'll tell you right there just by looking at it what direction the current is going, and it'll tell you which end is the striped cat, right? The negative cathode. Plus and minus indicates a positive or negative voltage on a power source. Source, gate, and drain are terminals to a field effect transistor. Base, collector, and emitter are terminals on a bipolar transistor. So I've just given you the other three, what those are, choices they give you. And that's right, electrode, diode. The whole idea here is ODE. ODE is used all the way around. The electrodes of a diode, an anode, and a cathode. That's right, Dean. That was another way that I remembered it too, was ODE. Which of the following could be the primary gain producing component in an RF power amplifier? So if you remember, we talked about a transistor can amplify a signal, right? The signal coming out of a transistor can be greater than the signal that comes into a transistor. And here clearly it mentions the word amplifier. Gain producing. Transistor is the only component in this list that has gain. The transformer may have a high secondary voltage ratio and can be used for increasing voltage, or it may have a high secondary current ratio and be used for increasing current. But these increases and decreases are called transformation or conversion, not gain. So the only other option that makes sense in this list is a transistor. Okay. So the A, turn it sideways, anode. Okay. I see what you're saying. That's good. And again, if you guys think of anything you see when you're looking at these, spit it, man. Let go of it, man, on the chat, because you know, one person will remember something. I can try to give you mnemonics, but it might not hook with you. Like I sat here and said, it tells you the direction because of the arrow. You have a negative side of it. It's right here. The stripe on it is, you remember, striped cat. But then Dean said, turn it 90 degrees, and you see the letter A for the anode. What is the term that describes a device's ability to amplify a signal? Okay, it's gain. Gain is defined as being the ratio of the output power to the input power. Or in other words, it refers to how much power is gained when passing through the transistor. Just remember that you gain a lot through amplification. Okay. What is the name of an electrical wiring diagram that uses standard component symbols? Well, we've been showing you these all night, and it would be a schematic. And the way that I remember that, I'm in IT, and I remember schema. Schema is a database term that I use a lot in work. But scheme, you know, you can have different schemes of an overall picture. So, you know, a device, your radio could have several schematic charts in it connected to it. You might have 10 boards inside of a radio. It's possible. And each one of them boards, them integrated circuit boards, IC boards, are going to be a schematic in itself. So the name of the electrical wiring diagram that uses standard component symbols is schematic or circuit diagram. But the exam is looking for the term schematic. Circuit isn't even in here. Bill of materials, I don't think so. Connector pinout. Okay, well, not all the components on a circuit board are actual connectors. Okay. Flowchart. Flowchart, you would think more in terms of a more theory than you would physical. Schematic would be more of a physical layout of a diagram, a physical diagram of the wiring. Okay. So the other options are terms also often used in a set of build instructions for a device, but they are not the wiring diagram, which is what the exam is asking about. A schematic is the scheme or plan for an electrical circuit or device composed of electrical circuits. So this is what one looks like. So let's look at it real quick. Okay. Excuse me. So we can tell right here we have inductors, right? The coiled wire, remember? There's a capacitor. And we can tell that's a variable capacitor because it has an arrow going through it. Now the antenna here, they use, it looks like just a little circle. There's actually a more definite symbol that they're not using here. These right here are capacitors. See the flat plates with the insulator in between? Here's another one. Here's another one. Resistors, you see the resistor here? So here looks like something like a switch, right? And it happens to be a key. You have a fuse. This looks like a transformer. We'll get to that in just a little bit. It looks more like a transformer. And then these lines right here, depending on, they could either be a ground or a power source. And we'll get to that one as well. So, and I picked this particular schematic because it actually lists and tells you next to them, you can kind of tell what they are. So this UF, that's farads, and that's what a resistor, or I'm sorry, what a capacitor is rated in is farads. That's the unit of measure. So anyways, what is the component 1 in figure T1? So when you're getting this test, we don't have much more to go. We're going to finish up Unit 6 here tonight. And when we finish up, we will be on par. We will be on pace, exactly where we wanted to be. Okay? But when you get this test, you're going to be given the test book with the questions in it, an answer sheet with all the little bubbles that you can make, you know. You're going to be given a white piece of paper, and then you're going to be given a paper that has 3 different schematics on it. Okay? And I've included that in the class materials. If you look under file sharing, I believe under supplemental test graphics right now, I'm sharing it. Okay. So look under file sharing, you should see that. Try reconnecting. Okay. So what is the component 1 in figure T1? Okay. So let's look at that. So this is figure T1. This is the one of them that you're going to be getting. So let's look at this. Okay. Remember the P in the pot or not P in the pot, so we know that's a transistor, right? There's the base, there's the collector, and there's the emitter. The emitter can either be going inward or outward. Okay. This is a battery. The reason why we know it's a battery, because a battery consists of plates or cells or mats. All 3 of them can be used interchangeably, but think of these as your lead acid batteries have a series of plates, and then the container is filled with an acid that charges those plates. And once a charge is put to it, those plates hold a charge. Okay? But number one here, that's what they want to know. Component one is a resistor. And I think the symbol in itself, does it remind you of, be reminiscent of resisting, right? You have a straight flow and all of a sudden it hits some kind of resistance, a rough spot. So, and the best way to remember that is, again, it's a nice smooth current and then all of a sudden it hits some kind of resistance in the path. So they're asking, what is this component? It's a resistor. Next one. What is component 2 in T1? Well, they've circled this one. You can remember the pot, here's the lid, the toilet, and the lid is a transistor. You have 3 points to a transistor. Okay, this is a bipolar transistor. So you have, again, the base, the collector, and you have the emitter. Component number 3 here looks a lot like a bulb, right? A bulb of some sort. So, what is the component 3 in T1? And figure T1. Okay? Well, the only thing it looks like, we know that's a resistor, we know that's a transistor. The ground symbol is going to be this fork here. You think of like a pitchfork you would stick in the ground, or a ground rods, a series of ground rods that are connected together. And the reason why they use the 3 is because typical practice for a lot of ham radio guys is to drive 3 ground rods into the ground and connect all 3. And those 3 will provide a path, will ensure more of a path of resistance. A path of least resistance for a surge to find ground. So 3 looks like a bulb, like I pointed here. Inside that little bulb, you see the filament, right? So this one's pretty easy. I mean, I think those 3 components kind of speak for themselves. What is component 4? It's the battery. And again, if you can think of, this is what the inside of a battery looks like. You got a series of plates here. These plates are connected at the top, but in between these are insulators. And acid soaks those insulators, and when a charge is put to this, these plates keep that charge. And it just looks like stacked plates. What is a component 6 in figure T2? Okay. So this is the second schematic that you're going to get on on a piece of paper. So let's go through these real quick. Number 2 looks like a fuse, right? Number 3 is a switch. If this arm here were to come down and connect here, it would complete the circuit. Number 4 is a transistor. A transformer. A transformer often gets confused with an inductor, but the way that you know that it is a transformer is once you see one, the wire is wrapped around. A transformer looks like a square piece of metal. And I'm going to show you a picture of one here shortly. But the capacitor, remember your 2 conductive plates with an insulator in between? What's number 8? What does number 8 remind you? Remember that? There's the diode, remember? The cathode end of the diode. And you have arrows that go away from it. That would be an LED. This right here is a perfect example of a variable resistor, a variable input resistor. This right here would be a great example for a potentiometer, a knob of some sort. This is a diode. And each one of these are grounds. So let's keep going. What is component 8? Well, you remember it's a diode, right? A light emitting diode. Well, those look like rays of light going away from it, right? So it's a diode, just like symbol 5 is a diode, except You know that this is an LED because the arrows going away from it would say something is being emitted. This component here is emitting something that's not coming back to the component, and it's not connecting to another component. That would be light. What is component 9 in figure T2? This is that potentiometer. It has a resistance to it, and the input, this is the user input for that. It's variable depending on a user's input on how much they turn this around. And the signal constantly goes through it, checking that input. So when you remember, when you have an arrow that on one side of a component that points back into the component, that's your telltale sign that it's a variable input. Okay? And they're a variable resistor. Okay? It couldn't be a capacitor because this is a capacitor here, number 6. If this was a variable capacitor, it would look like number 6 with an arrow diagonal through it. They ask variable inductor. Well, there is no inductor in this entire schema. Remember the inductor? It looks a lot like this transformer coiled wire. However, right here you have, once you see what a transformer looks like, it makes so much sense once you see it. What is component 4 in figure T2? So component 4, here's a transformer. Okay? Wire is wrapped on one side and it's wrapped on the other. Take notice in how on one side of this, dimmer switch in a dining room, okay? And that would be a good example, is a variable resistor. That's right. So primary winding, so if you notice the winding, the red wire here is wrapped around more times than the secondary wiring. Okay, and the core of the transformer is representative of these two solid lines here. The wire is wrapped on on each side of this solid core here. Look at the picture here. Now, does it make sense that it looks like a transformer, right? Once you commit it to memory and you see it, you're like, oh, okay. See if I've got a picture of a transformer. I think we'll get to one. What is the component 3 in figure T3? Okay, this is the third and only, this is the last schematic chart that you get on the test. There's only 3 of them. Okay. Now, this could have been a transformer, right? However, the difference between a transformer and an inductor is a transformer has the 2 solid cores and wires wrapped around each core. So there would actually be 2 of these side by side with 2 solid lines in the middle. Remember, the arrow is going back into the component. So the component tells you that it's an inductor. The line with an arrow going back into the inductor tells you it's a variable inductor. Now, this right here is a variable capacitor. If you take the arrow away, now why doesn't the arrow come back into it? I think the reason why is because these two don't, this is a component where they don't actually touch each other. There's an insulating property in between them. Okay, so these both are variable capacitors. This is a variable inductor. Number 4 is an antenna. Looks a lot like rabbit ears, doesn't it? Remember the old rabbit ears on top of the TV that mom and pop would make you get up and move around so that they got Romper Room or they got the Lawrence Welk show in better. Yeah, I'm not a baby, so I'm not a youngin'. That tells you. I grew up on the old Lawrence Welk, and anyways, you had to get up. You were the tuner for your TV, for your family's TV. And this is what an inductor looks like. So there's a little screwdriver or Beth, I didn't want to go there. I didn't want to get so ghetto on you guys, but yeah. Or you didn't even have the rabbit ears. Your rabbit ears were foil. Or it was the antenna shoved down into the broken telescoping antenna. It was shoved down in it. And that was your rabbit ears. Okay, I'm old. Yeah. Oh. And so the variable inductor would take a screwdriver on the top here, and as you turn this, there's your wire right there. Okay. Wire hangers. What is component 4 in figure T3? Again, looks like rabbit ears. So that's a really easy one to remember. And that's why I was telling you, like that one schematic that had an antenna as a little circle, that's not necessarily a true, what do you want to call it, industry schematic. This would be more industry standardized. Every time I've seen a schematic, this is what the antenna they used, it looks like on it. What do the symbols on an electrical schematic represent? So let's be clear about something. It is the electrical components, but a schematic only tells you how they're connected, not where they're physically located. Okay? So if you were to open up a device, you're not going to see a rectifier sitting next to a transformer. This transformer inside the box could be towards the very back box of the box, and the rectifier could be in the very front. It doesn't tell you where it's physically laid out. It only tells you how they're connected to each other. And so whoever creates this schematic is going to lay it out where they can fit the components. That's all. So it's not going to tell you where they're physically laid out, just how they're logically connected. Okay. Which of the following is accurately represented in electrical schematics? So like I said, the way the components are interconnected. Okay. It doesn't tell you where they're located. So I know this little thing here, this little schematic symbols thing, it really doesn't make sense for this question, but I had to fit it in somewhere. If you can remember all of these, if you can remember these and commit to these, what these look like, you're going to pass the test because you're only going to be tested on these. Okay. They don't have the diode up here, but they do give you the diode and the LED. Okay. And they don't put inductor on here for some reason. But if you can remember transformer, it's not hard to remember the inductor. But I just wanted to put this in one. Oh, there goes a variable inductor. Derp. Okay. So variable, if you take out the arrow here, it would just be a straight inductor. Here, if you took out the arrow here, it would be just a straight resistor. So if the arrow is pointing in to the object, that's a clear sign that is a variable. If the arrows point away and they don't point to another object, it tells you that that component emits something. So why aren't there arrows coming off of the antenna? I don't know. I don't have a good answer. Which of the following devices, we're almost done here. Yeah, I mean, that's what I was saying, like schematics, you can have like, so on my 7300, the owner's manual, it actually comes with a book of the inside of the radio, the schematics for the radio, and it's like 30 pages for my radio. But when you open it up, there's only like 2 boards inside of it. Okay. So sometimes it takes more than one sheet of paper to completely explain all the components on one single IC board, integrated circuit board. So which of the following devices or circuits changes an alternating current into a varying direct current signal? Okay. So we basically know so we know that an amplifier is basically a transistor, right? That couldn't be it. So let's go look here. So a rectifier is a component that uses diodes. And this is how it looks, right? It looks like a series of diodes. And there's usually on a diode, there's going to be a lead that comes off of each corner of it. And ironically, here's an example of what a rectifier looks like with its 4 leads. A rectifier is a component that uses diodes to direct all current down a specific path. So a transformer is a component that changes the voltage scale of a signal. It can convert it up or it can convert it down. So your radios, if you use them in your car, you don't really, a power supply that you would use in your house to connect those radios to your house, that power supply, basically, you could make your own power supply if you understood electronics but the main component of that power supply is going to be a transformer, because the idea is your radio, it's looking for 12 volts, but what's coming out of your wall is 120. So it needs a transformer to step down from 120 or 110 to 12 volt. Okay. So an amplifier is a component that amplifies. A reflector is usually part of an antenna. So an antenna, you ever heard of a Yagi antenna? If you remember the old antennas you had up on your roof for TV, they were on your roof, and you had some rods that were longer than others. The longer rods are reflectors, and the shorter rods are directors. And usually the antenna looked like it pointed in one direction. I think you guys get what I'm saying. So I put all this together. I just wanted to give you an example of what these could look like. So this right here, that symbol alone right here looks a lot like a transformer. I mean, this symbol, this piece right here looks like a transformer when you look at this. The power supply usually is going to have an S in the middle. Looks like an S. The capacitor is just this. So the capacitor is going to be this piece right here is the capacitor that they're pointing to. The rectifier is going to be this board right here on the other side. So I just wanted to give you a pictorial representation of what it might look like outside of a case and all that. What is a relay? So a relay is just a transformer, okay? Relays are used extensively in vehicles. Whenever you flip a switch that causes something to happen, it will most likely be controlled by a relay. Okay, a relay allows a fairly low energy source to drive an electromagnet that closes a switch designed to handle a much higher energy source. For example, a relay may only need 100 milliamps to drive a relay that can handle 10 amps. And so what I did here was I gave you the example of what a relay looks like in your car, and this is what inside one of these looks like. So you see here we've got 5 leads, and you've got 5 leads on the, and 2 of these are going to be, I'm probably going to imagine that these top and bottom ones are going to be your terminals for contact or no contact or NC. And here on the top here, the diagram they give you, so they give you a somewhat of a diagram of it. So what type of switch is represented by component 3 in figure T2? Okay, so they give you several here: single pole, single throw, single pole, double throw, double pole, single throw, double pole, double throw. There's only really 4 main types of switches, and they've managed to list all 4 here. Well, here's the deal. They're really not all that hard to. So here's the confusing part maybe. This little rod here, that's the throw. It's not the pole, but it looks like a pole, right? The red here is the throw. The green here are your poles. In electronics, poles are another term for contacts, okay? It's not a physical pole. It's usually a soldered contact point that is raised up on top of a circuit board. And that's where the term comes from. So the greener poles and the red is the throw. Okay. So we've already looked at this before. We've already said like I believe number one's going to be, it looks like maybe your power source, or it's going to be a, I have to go back and look. Number two is going to be your fuse. Number four is your transformer. 5 is a diode. 6 is a capacitor. 7 is a resistor. 8 is an LED. 9 is a variable resistor. And number 10, I'd have to look to see what that one is. It's not a variable diode. I'd have to look what that is. And here is this little circle here. They don't have it numbered. I think they're trying to represent an antenna. So anyways, so let's move on because I'm going to show you. So here's the difference, okay? And it really depends on what you need the switch to control. So some switches are 3-position switches. Okay. And you might need it to do one thing, and in the middle the switch is off, and then you turn and you flip it the other way and it does a second thing. So if you look at this diagram here, so single pole means that there's a single set of contacts that are connected and disconnected with the switch. So notice that there's only a single line into the switch and a single line out. Okay. Double pole would mean that the switch could connect or disconnect 2 wires at once, and there would be 2 contacts going to the switch. Okay, like we have in this one. Single throw means that there's only one choice for each of these contacts. With a double throw, the switch would connect the input to 1 or 2 outputs. Triple throw would be 1 of 3 outputs. Typically, you don't see a triple. Typically, most switches that we deal on a day-to-day basis are going to be a single pole or a double pole. I thought it might have been a plug, right? Yeah, I thought that might have been like the prongs. I thought that might have been, like I said, I thought it was power. They believe I said that. I've seen it use 2 lines, or I've seen it with an S. So I thought that might have been power. So which of the following displays an electrical quantity as a numeric value? We're almost done. Give me just a few more minutes, and then I want to be caught up on section 6. So a meter would display some kind of a numeric value for an electrical measurement of quantity, right? I mean, we've got potentiometer in here. We got meter there, but that's a variable resistor. A meter in this case is a device that measures something and displays the results in some form of numeric scale, either a needle or a digital numeric display. So a signal strength meter, a voltmeter, an ohm meter, a thermometer, and I've given you the other three choices that they give you. I explain what those are, and they are electrical components that affect the flow of electrons in a circuit. They don't measure a circuit of any kind. Okay, so I just gave you, here's an amp meter, a voltmeter, and then a digital meter. Okay. What type of circuit controls the amount of voltage from a power supply? So when you think of control, you can think of regulate, right? What does the government do when they put a regulation on you? They control you. So what type of circuit controls the amount of voltage? So what type of circuit regulates the amount of voltage? I think in this instance, the question is in the answer, right? They're synonymous with each other. So a lot of times you'll hear of a voltage regulator. So, it regulates the voltage down to a particular point. And then I give you the other three, what those are. So an oscillator generates an electrical signal. A filter does signal processing. It removes or it enhances certain frequencies. And a phase inverter splits a signal that produces two outputs, one of which is identical to the input and one is a mirror image flipped. So I have a pair of headphones, really high-end headphones called Heil. They're very, very good. So you can always look up Heil headphones. And it's got a phase switch on the side of it. And sometimes when I'm listening and I hear a lot of static and a lot of interference, I can hit that phase switch and it will change the shape of the audio. And sometimes it improves the signal for me. So it either brings the left or right channel in phase, brings the right channel in phase to the left one or out of phase. What component is commonly used to change 120 volt house current to a lower AC voltage? Well, it transforms it. Usually a power supply, regulated power supply is regulated through a transformer. Again, here is, you got the input voltage, it's got much more wires to it, and it's reducing it down to a lower voltage output-wise. And there's not as many windings. And this is an example of what a transformer will look like. So the ratio, the number of turns of wire around the magnet determines the input and the output. Which of the following is commonly used as a visual indicator? So out of all these, we would use an LED to give us some kind of indication. The power's on. LED might go off if you reach a certain threshold. You see it on soundboards if it clips at a certain, certain volume. So out of all these, LED is the only one that is used for the purpose of visually indicating something. So just remember, LEDs do tend to have a much lower power consumption than traditional incandescent or fluorescent bulbs used in your house. So, which of the following is combined with an inductor to make a tuned circuit? So the best way to remember this is to remember the two components that store energy in some sort of field. One's an electric field and one is a magnetic field. Now, the best way that I remember this is a tuned circuit. So what is a radio wave? A radio wave is an electromagnetic wave, right? A capacitor stores the electro portion, and the inductor stores that magnetic portion. So electromagnetic, when I think of a tuned circuit, it would have an inductor and a capacitor within it to do that. This is what an inside of a tuner can look like. I showed you one of these components earlier in the evening. A tuned circuit. So this would be what we kind of call an LC circuit. So just remember, see, I tuned it. All right, see, I tuned it. Capacitor plus inductor equals tuned circuit. See, I tuned it. C and I. What is the name of the device that combines several semiconductors and other components into one package? So an integrated circuit is just a package. Again, it's a collection of components to make the entire circuit. Okay, so your typical silicone chip, CPU, this is what one looks like with the silicone burned away from it and the inside of it. You see all those little circuits inside there? They're almost microscopic. Okay, that in itself is an integrated circuit. So an Intel chip or an AMD chip, or anybody that's ever built a computer or anything, everybody knows Intel, right? Intel computer chips. And this right here would be a component, would be an integrated circuit. So you either have a microchip or complex integrated circuits would be, it could be a series of CPUs, microchips, diodes, capacitors, transformers, inductors could also make up an integrated circuit. What is the function of component 2 in figure T1? We're almost done here. I'm surprised we haven't hit the end yet. Component 2 in figure 1 is control the flow of the current. So what is the function of component number 2? So a transistor controls the transition of a current, right? Current transitions into a transistor, either comes in at one power and it transitions out of it at a different power, either lower or higher, either amplifies it or switches it. So again, we have the base. Here's the base, is the green. We have the collector, which is the blue. And let's make purple the emitter. Okay. It's the only symbol in the diagram that shows a signal that can have multiple current flow possibilities. In this particular diagram, everything else has one thing coming in and one thing coming out. This one, it has a signal coming in and it has a signal coming. It can take either route. It can go to ground or it can transform it to another power, to another voltage or whatever. Which of the following is a resonant or tuned circuit? It's when an inductor and a capacitor, remember, tuned circuit. See, I tuned it. So only one of these answers has an inductor and capacitor in the name. An inductor and a capacitor connected in series or parallel to form a filter. A tuned circuit is a common name for a resonant circuit made using a capacitor and an inductor. Here's the inductor, the wire coiled, and here's the capacitor. The insulators are the air in between these plates. And these are a series of capacitors. Resonance occurs when the effects of capacitance and inductance in a circuit are the same. This is what I like to call the sweet spot. Which of the following is a common reason to use shielded wire? So what they're talking about here is on coax, we have usually a foil, and depending on the quality of the coax, the more shield it has to it, it's like anything. If you've ever had to play with mess with electrical wire, if it's shielded, this one right here has a series of 1, 2, 3, and possibly 4 shields to it. Not much signal is going to get out from the inside of this, and not much signal is going to get in and interfere with this electrode, right, or the conductor. So not only does the shield keep the signal from this conductor from leaving the wire and interfering with other things, but it also keeps interference from outside the line from tickling this conductor and creating some interference. Okay. That's it, fellas. Section 6 done. Next week, we're on to section 7. We are up to date. We are caught up. We are right on cue right now, right on where we need to be. So with that said, any questions tonight? Any questions that you made note of that you want to ask me? Yeah, Beth, that's what I'm saying. We are on cue. Like, I wanted to be at each week. I wanted to be at a section, and I told you we were a little bit behind. And I said I'm pretty confident we're going to get right back on pace. And tonight we did it. So thank you so much, you guys hanging in there. We ended up being 2.5 hours, and you guys hung in there for me, and I thank you so much for that. Sometimes it's really hard. I don't want to zip through these and not give you guys explanation, but I walk that fine line, right, between giving you enough information that helps you and then staying on one thing too long and wasting time. So it's like a tightrope dance with me. So anyways, any questions that you have, I'm here for you. Ask them now if you'd like. You can, let's see, hamtechclass@gmail.com, mercury01@preppernet.com. Those are the two that you can. Well, you know what? You guys are doing a good job. I mean, really, this stuff is, you guys are really the ones doing a good job. If you're absorbing this and I'm keeping your confidence and you're able to say, you know what, I got this. I really can do this. Then we're a success. If you walked into this completely lost, had no idea about ham radio, and you feel that at the end of this class, you have so much understanding of repeaters, how to calculate power or resistance, then it's all for the. Yeah, Lee, I agree. That's the mnemonics, like I said, the toilet, the pee into the pot, and no pee in the pot. I mean, man, I would never remember that NPN and PNP if I didn't think of something silly like a toilet. Yeah, any questions? Anybody have any questions you wanted to ask? I guess Eddie didn't make it tonight. I missed him tonight. Dean, it was good to see you, and see a couple of the others, John and. Any questions? Okay, so I'm going to let you guys go. Email me if you have any questions. I hope that I've given you all the materials that you need to help you along with this. Go back, watch the replays as you have the test questions in front of you, and follow along again. And if you're like me, a lot of times you have to watch something several times and you pick up something different each time. So what's up, Richard? You got a question? You said no, Natty. You got a question? Yeah, you have a good night too, Leah. Cool. Yeah, Paul, like I said, it sounds like you guys are learning. You're never going to be a guru at this until you actually key up the radio. Again, think about this. I may not be giving you the most scientific answer, but the most scientific answer is most surely going to lose you. I'm just trying to give you the ways to be able to remember the answer that the FCC's already given you. I'm just trying to create creative ways for you to remember them. That's all I'm trying to do. So how do we get the replay? So Paul, again, if you should get emailed after this, if you registered for the class and you got the reminders right before the class with the links on them, in a couple of hours, you will get a replay link. Don't worry about what week it says. Don't worry about that. I didn't update it, so it's probably going to say like week 4 or something like that. Please don't worry about that. It applies to the week that you get it. So in a couple hours, you'll get one, and it's meant for tonight. You can do that, or you can go to PrepperNet.com/tech. I just typed it in there. Okay, good. You got the reminder, so you should get the replays. If you go to this, what I just typed, preppernet.com/tech, you have to register for, it's a free basic membership to PrepperNet, but I think that you'll like what you see in PrepperNet. You might become a premium member. But you need the basic membership and get a login and all that to get access to the class page. And on the class page, it has all the materials for the class. All the materials. There's no other, it just, all the materials are there. It's got test questions, every last one of them. And you'll see the videos that we've recorded. I've got last week's and this week's, I've got to update. All the PDFs up till tonight are there. So the 5 sections, the PDFs of these PowerPoints are there. I couldn't give you the PowerPoint because it's copyrighted material with PrepperNet, and they didn't. PrepperNet didn't want you to be able to go in and alter and then reshare the material, so they own the rights to it. So I've given them complete ownership of the class. So par for the course. I didn't pay for the interface. So just to let you know, this interface that we're using, it runs about $500 a year. So you got it free. Somebody had to pay for it, and that was the owner of PrepperNet paid for it. So for his rights in paying for the interface, the trade-off was that he got to keep the class for PrepperNet. I don't technically own it, so. And you'll have everything there. We'll get the page updated with tonight's video section. I think it goes 1 through 4 for the videos. I got to put 5 and 6 on there because we went through 5 and 6 tonight. But the PDFs, the PowerPoints, there's 1 through 5. I've got to put 6 on there. So 5's video is missing, but the PowerPoint is there as a PDF. And then you got the test questions and the graphics, those figure T1, T2, T3, the schematic things, they're on there. Just everything should be there for you to, you're not paying a dime, except when you take this test, it'll cost you probably anywhere from $12 to $15, and that's all you're going to pay to get your ham radio license, unless you go out and get a book to help you. All right, guys, if you have any questions, hit me up on email, and I'll get back to you when I can. Hopefully, I check it every day, so hopefully I do. Other than that, we will see you next week. Same Bat Cave, same Bat Channel. We will talk to you guys later. God bless and stay safe. Bye-bye.